Okay, hello and welcome. I thought I would, as I mentioned earlier, instead of doing the lab, go ahead and do a little video of kind of the thinking process of running the test. So I'll break it into two parts. Let me do the multiple choice first. And so let's begin here with number one. The first one says, how many millimeters are there in a kilometer? And of course, this goes right to chapter one. This is about the prefixes. This means a thousandth, and this means a thousand. And so, of course, what that would mean is you would need 1,000 millimeters to weigh 1 meter, and then a kilometer is 1,000 of those. So this would be 1,000 times 1,000, which is 6 zeros, which is the million. So I guess the answer would be D. D is in dog there for number one. Number two says, what is the height of the ceiling of this room? Now, I know you're all in different rooms, but of course, this problem is thinking about a lecture hall. But whether you're in a lecture hall or not, these other ones make no sense. B, C, and D are just unreasonable. And that's really what this is after. You don't have to know exactly the room. And I hope you didn't bother to go out and measure the room. This was a one to test if you kind of knew roughly idea what these were. This is the correct answer would be A, so I'll skip it, but we can rule out B. B is about 30 centimeters, and 1 centimeter is about this much. 30 centimeters is about the size of this piece of paper, so that's clearly not the height of any room, so we'll rule that one out. So it's definitely not B. It's also definitely not C, because C is actually the same as B, 300 millimeters. There's 10 millimeters in 1 centimeter, because this is a thousandth, and that's a hundredth. So those are the same size, which is the size of this paper. And then this one's huge. This is a kilometer, and put it that in meters, you would move the decimal 3, and so that's 30 meters. And so a rough idea here of a meter is about the height of a table, and so from the floor to the table. And that's why a ceiling's about 3 times that much. So anyways, all of that is to say, hopefully you put A. A would be the answer there. Everything else is just unreasonable. Which of the followings is equal to? So again, from chapter 1, this is our scientific notation, and you would move the decimal 4 to get it over to here. And so that means you would write it as the 8.64 and then times 10 to the 4th, how many decimals you moved. And so that would be B here. The B is in boy. And then one more from chapter 1, a unit conversion. We're not actually going to convert any units. It's just going to set it up here. It says, but given that a mile is about 1,600 meters, I think actually 1,609 is a better number here, but about 1,600 meters, which calculation would show the conversion from miles per hour to meters per second? And so the first thing you would start is miles per hour, and they all do that. And now you got to convert both miles to meters and hours to seconds correctly. And it looks like they're going down the road of hours and seconds. And so if you look here and you look at this next one, which is an hour over a second, this is I was showing. This is essentially multiplying by 1 because you have the same thing in the numerator as in the denominator. And so this technically doesn't change anything, except it changes the units. And so where it would be appropriate would be right here. Hours would cancel with hours, and you would be left with a second down in the bottom. That's good. That's what we'd want. The second one would do the same thing, so everything's still good there. But you can see that the third one here, the C messes it up and D messes it up. You get hours on the bottom twice, so you get an hour squared, and it doesn't cancel off. You don't get rid of the hours and convert it into seconds. So at this point, the only options we have are A and B, and then the same thing here that, again, we need to multiply by 1, and again, 1,600 meters over 1 mile, or 1 mile over 1,600 meters would be the same thing. They would be a ratio of 1 because they're, the numerator is the same as the denominator. So here we're not changing anything. We're multiplying by 1, so that's good. But we need the right units, and so here we need to put miles on the bottom. And so if we put miles on the bottom, they would cancel. And this one shows meters per second, whereas the second one is going to be messed up because we'd have miles times miles. In the top, we get miles squared. per meter. So that leaves us with option A. And as I said, there would be 4 from Chapter 1, and those are from Chapter 1. Here is Chapter 2, excuse me, question 5. It says an object is accelerating only when its speed is changing. Well, this was the definition of acceleration. Acceleration is a change in velocity. And velocity is both speed and direction. So either one could change. So it's not just only speed, but it's not B either, only direction. It is when it's speed or its direction. And so if either one of those changes, which also implies if both of those are changing. So anyway, C would be the correct one because it would be a change in velocity. These other ones would not be velocity. Which also then fits with C. C is kind of the same thing. So what is the, quote, accelerator on a car? I even mentioned this one in class. And so anything that would make it go faster or slower, that's a speed change, or change its direction, which would be the steering wheel, would be an acceleration. So brake pedal makes it go slower, gas pedal makes it go faster, and then steering wheel changes its direction. So slower, faster, change direction, all of those are an accelerator. And so the best answer is D. And again, another one from Chapter 2. It says here, the motion of a ball or a cylinder rolling down a ramp is one of... And we did some video animations of this, and hopefully you saw it, but the slope of the hill determines the acceleration, as I said in Chapter 2. At that point, we didn't have enough physics to really understand that, but we do now. So if you had an incline like this and you put a ball on it, the force of gravity, which we've labeled as mg, like that. But we learned, and not in this Chapter 2, it was later on, I guess, in Chapter 4, where we did motion in space, we could think of that as partly down the hill and partly into the hill, perpendicular. So it's like, this is like the x-axis, and this would be like the y-axis. And so we would have kind of a tilted axis, if you will. But the point is, since the force of gravity going down is a constant, this component would be a constant. So we'd have a constant force resulting in a constant acceleration, because acceleration equals F over m, which again is Chapter 3. So if we take Chapters 4 and 3 and put them together, we can understand why this is a constant, but you don't have to even really do that much. You can just go right to the reading of the book, and even in my lectures I said it was a constant acceleration, and definitely was not a constant speed. It kept going faster and faster and faster. And even though it went faster and faster and faster, that is not an increase in acceleration. That is an increase in speed, so it's not B. It is, again, C, constant acceleration. Okay, well, going to the next page here, which is problem numbers 8 through 12 when I printed it here. It says, oh, you know what? I'm going to go back so you guys can see that. I meant to look before I changed it at the screen and make sure you can see all the answers. And I forgot to look here. But anyway, so there it is in case I did miss it. But I don't think I did. Okay, so I'll look at the video when I'm done here. All right, so let's try this one, and let me kind of set it up so you can see here. But again, I think this one is from Chapter 2 also. It says, suppose you are looking out at the 10th floor window and you see a ball falling at 5 meters per second. How fast will be the ball falling after 1 second? And so the point we learned here was that a falling object has an acceleration of 9.8. It was the first lab we did and measured. I'll just round that to a 10, and so that's just saying it would gain 10. So if it had 5, then a second later it would increase by 10, and so C would be the correct answer there. This brings us into Chapter 3. 1, 2, 3. I think the next 4 here are from Chapter 3. It says the property of an object to remain at rest. This is Newton's first law. It's why we called it the law of inertia. That description right there, the resisted state of motion, is the fundamental definition of what inertia is. And so that's the B. That's the property. It has inertia. 10. If an object moves in a straight line with a constant speed, we can conclude that. And so again, this is the first law. We know if something has a constant speed, there is no net force. There is no unbalanced forces acting on it. And I believe that is how they're going to phrase it here in D. Object has inertia. Well, that's just it has mass, and anything could be, could be going faster, slower, turning, or straight line at a constant speed. There are no forces acting. No, that's not true. We can't conclude there are no forces because there might be like two equal and opposite forces, so the net force comes out to be 0. So we can't say that there are no forces, although no forces would make it go in a straight line at a constant speed. So that's true. So be careful with that one. That's probably the sucker one here because it's true, but that's not what we can conclude from this. There must be at least two forces. No, we could have none like up here. Now, we know we couldn't have one force because one force, you could never get the total of one force to come out to be 0. But two forces, if they're equal and opposite, would. In fact, three forces, if they kind of came into an equilateral triangle, could all three add up to 0. And 4 could add up to 0, and 5 and 6. So basically, to get this, we know that the net force is 0, which could be no forces, or 2, or 3, or 4, but not 1. Anyways, but that's not true, see. And so we're, finally left with really just D. There is no unbalanced force. That sounds funny. There is no unbalanced force acting on the object. Oh, yeah, there is no unbalanced force. So the forces are all balanced. Right, D. Okay, so that just reads a little funny there. At least it did to me first. All right, moving on here. If you leap from a bridge with a bungee cord tied around your ankles, as you approach the river below, the bungee cord begins to stretch and you begin to slow down. And here is the whole question, and this is Newton's third law. The force that the cord puts on your ankles to slow you is blank to the force your ankles put on the cord. Okay, so the force the cord is on your ankles. So those are your two objects. The cord is putting a force on your ankles, and then your ankles are putting a force on the cord. Those two must be equal and opposite. Doesn't matter how fast you're going. Doesn't matter if you're slowing down. Doesn't matter if you speed it up, right? Newton's third law just says those two forces are always equal and opposite. And so they must be equal to the force. That's Newton's third law. And so B. And then I think this is a Newton's third law too. It says two skaters then face each other. Oh, this is one that you had a homework on and we talked about in class. But this is one where the two skaters face each other on perfectly smooth ice. One skater has twice the mass of the other. Assume that the bigger one pushes the smaller one, which is true. So if I put a big one in the homework one you had a mother and daughter. But the third law says whatever force the one puts on, the other one has the same amount. It doesn't matter about which is bigger. I mean, who quote unquote does it here. This one says the bigger one pushes on the smaller. So the bigger one pushes on the smaller with the force F. Okay, but then the smaller one is pushing exactly the force F there. And so the acceleration of number 1 and the acceleration of number 2 aren't necessarily the same, because even though the forces are the same, to get the acceleration, we would be dividing by the mass of that. And then that's where bigger and smaller comes into play. And so the bigger person would have a bigger number down here and a smaller acceleration, whereas a small person would have a smaller mass and therefore a greater acceleration. So which is the following is true? Here it says the bigger skater won't move. No, that's not true. The bigger one does have an acceleration. The bigger skater will move with a smaller acceleration. Yeah, that one is true. The bigger skater will move with a larger acceleration. No, that's not going to happen. Both skaters will move with the same acceleration. No, same force, but not same acceleration. So don't confuse force and acceleration. So it looks like then B as in boy would be the best answer for number 12. All right, page 3. All right, so moving on here to page 3, and see, let me adjust the video here, or the camera. Okay, So, here we got circular motion. So this is right at it, chapter 4, and motion in space. And so this race car here is moving in a counterclockwise direction. And hopefully one of the things you got out of chapter 4 is there needs to be what we called a centripetal force, a force towards the center of the circle. This thing is accelerating. Now, it's not going faster or slower. That's what it says. It's a speed of 100 miles an hour. But it must be pushing sideways to the direction it's moving. That's that little diagram you keep see me doing on the board, where I say, okay, if something's moving this way, and you apply a force in the direction it's moving, it goes faster. But if you apply a force opposite to the direction, it goes slower. And if you apply a force perpendicular to the direction, it makes a turn. And that's what this is. This would be a turn. So it'd be towards the center of the circle. So looking at this, what direction is the net force? It must be D, because it's pointing perpendicular. Well, and then towards the center of the circle is probably the best way to say that. Here we have an object. This is a bunny moving to the east. So I'll draw a little arrowhead. So bunny's going this way at 8 meters per second when the bunny then sees a fox. And then the next half a second, the bunny then changes its velocity to west. And so now it's going that way at 12 meters per second. The question is, what is the magnitude of the bunny's average acceleration? Well, acceleration is the change in velocity and the time taken. And so be careful with both parts of this. I think one of the hard parts is to realize this is a change of 20 meters per second. In a number line, you might say we're going from a +8 all the way to a -12. And so, in other words, the bunny has to slow down and lose 8 and then go the other direction, 12. And again, that's a change of 20. We lost 8, and then we gained another 12. And so the bunny's gone a change of 20 towards the west. And now we don't have to care about direction because it says what is the magnitude, but it is to the west, a change of 20. And an acceleration is measured how much per second. So the second half of this is to realize that the bunny is changing at a rate of 40 meters per second each second. Not that the bunny changed by 40, the bunny only changed by 20, but it did it in a half a second. So the rate is 40 in 1 whole second. And so had the bunny kept accelerating for 1 whole second, the bunny would have changed by 40. So the correct answer then would be this D. That's the rate it's changing by 40, not by 20. It did change by 20. But I can see how it would be easy to put an 8 here, because you might think, oh, this is just a change of 4, and then a half a second. So that's why the 4 is there. And then a half a second, well, then you'd get 8, but both of those would be wrong, and even C would be wrong. It's D. Again, also from chapter 4 here, this is a 2-kilogram ball is thrown horizontally at a speed of 10 meters per second. And at the same time, a 1-kilogram ball is dropped from the same height, ignoring air resistance. Which ball hits the ground first? And the answer is a tie. The whole point of chapter 4, this motion in space, was to point out that it doesn't matter that it had horizontal motion. The key here is it's throwing horizontal, so it doesn't have a vertical speed. And, of course, the ball's dropped, so it also doesn't have a vertical speed. So, essentially, in the vertical discussion, forgetting the horizontal, that was the whole point, that we can ignore horizontal motion in our two-dimensional motion. Both of these have no vertical speed. Both of these are essentially just being dropped vertically. One literally is being dropped, no horizontal speed, but the other one does have a horizontal, but we can ignore that for the sake of a discussion about the vertical. So they both have no vertical speed to get start with. And so they'll fall at the same rate. Now, also, I guess, added to this goes back to chapter 2, where we said all objects, whether they're 2 kilograms or 1 kilogram, have the same acceleration of 9.8, roughly 10. So the fact they have different masses is just kind of irrelevant. But, of course, put there to see if that's what you conclude. Are they irrelevant? All right, well, continue on. I think, again, more about two-dimensional motion. Here it says a car drives off a vertical cliff. So maybe I'll make a little cliff here, kind of Say, okay, here's the car and it drives off the end, so it's going to, and fall down to the bottom. But this is a lot like this one where we probably can, conclude that it goes off horizontally here. So it drives off the cliff at 24 meters per second. And again, this is this two-dimensional motion. It does say it takes 3 seconds for it to hit the ground. So the cliff is substantially high enough that it's going to take 3 seconds. And if you remember from class, we worked out that that would be 45 meters. You don't really need to know that. The 3 seconds is enough, because what you just need to realize is that the horizontal speed won't change. So it would go 24 in the first second, it would go 24 in the second second, and it would go 24 in the third second. And all of that add up to 72. And so it would go 72 meters. And so the answer would be D. That's how far it's going to go in 3 seconds. And the fact that it fell down 45 is just a consequence of the rate of acceleration. And that would have been a harder problem had we needed to figure that one out. But that wasn't the question. And then, of course, this one says, which of the following statements about the moon is not correct? And so, this must be chapter 5 on the universal law of gravity. The acceleration due to gravity on the moon is weaker on the Earth. And that's true. You had a homework problem to show how much somebody would weigh. There was also a reading in there that the weight is 1/6 on the moon. And probably even before this class, you probably didn't need to be told all that. Most people get the idea that, the moon has a lesser force of gravity on it. So it's not A. The Earth's gravitational pull on the moon equals the moon's pull on the Earth. Yeah, that's Newton's third law. Equal and opposite. So if the moon pulls on the Earth pulls on the moon. It'd be equal and opposite. So that's, again, really a chapter 3. And so it's not that one. There is a net force acting on the moon. That would be true also, because we know that the moon is going in a circle. And so as it goes in a circle, it would be both accelerating, and that acceleration would have a force on it. Which is why then we get to this last one, D, the moon is not accelerating. That's a false statement. And of course, one thing that makes these multiple choice hard here is it's asking for which one is not correct. And so A, B, and C are all correct statements. It's D that is an incorrect statement. And I think it's kind of a tempting one, because we know that the moon doesn't go faster. That's not why it accelerates. The moon is accelerating because it changes direction as it goes around, and it takes the roughly 28 days to go around. And so that's the idea, that it keeps going the same speed, but it goes around in a circle. Anyway, so that would be D. All right, and then on to page 4, and the last page here for what I'll just make a little video here for part 1, and then I'll make a second video with the free responses here. But on to 18. Yeah, now personally I think this is the hardest of the multiple choice ones. Maybe even harder than the free response ones, although it's probably a tie with one of those in there. But here's our astronaut, Skip Parsecond. He visits this planet, MSU, which is composed, and here's the key, it's composed of the same material as the Earth, but has twice the radius. Okay, keep that in mind. Because then they go on to say that Skip weighs 800 on the Earth. And then how much is Skip going to weigh when he's on this MSU-8's surface? All right, well, starters, maybe we'll do like the homework problem, where the homework problem had one, and this is close, but not the same as a homework one, where you had doubling the distance. And the universal law of gravity had the distance between them. And so in the denominator, there is a 2 squared. And so that alone, you would say that the weight has been reduced by a factor of 4. So that's part of it, but not the whole story. Now, in the homework problem, they said that this planet that you were on had twice the radius, but it had the same mass. That's not quite what they said here, and that's what might make it a little bit harder, because you might have read this a little too fast and said it is composed of the same material. And so you might have said, oh, well, it's the same mass. And no, it is not the same mass. Maybe I'll do this. I'll draw a little box. And if I let that box kind of represent the Earth, and I'll try to draw a three-dimensional box. And so I'll draw a box instead of a round object, because I think it's easier to see with a box. But if you then take that box out of the same material, but you make it bigger, and so I'll make it at first twice as wide, you're not going to have the same mass. Now its mass goes up. And so now it's twice the mass. And we're not done, because it says when you make it twice as big, you got to make it twice as tall. And so I'm hoping this looks like kind of a three-dimensional stack of 4 blocks. And so again, the key is it's the same material. And as you start stacking more blocks here, the mass goes up. So we're going to have to change a number in the numerator up here, whereas we didn't on the homework. The homework was a little bit easier. It said it's just the same mass. And so all we focused our attention on was the one in the bottom. All right, so I've made it twice as wide and twice as tall, and that makes 4 boxes. So this right now is 4 times that of the Earth. And then if I can add kind of another set of 4 boxes behind that, and so it would be twice as deep. So it's twice as wide, twice as tall, twice as deep. And so if you make it, you know, the radius 2 times bigger, and of course I drew boxes because I think it was easier than to show a sphere. But if you change those to spheres, we would have 8 of them. And so this mass goes up by a factor of 8. And 8 over 4 is a factor of 2. So Skip actually weighs more on this planet by a factor of 2. And so 2 times 8 is 16. And so there is C for answer 18. And so, like I said, this is a hard one. So don't beat yourself up if you miss that one. That one is just downright hard. But if you got it, yeah, pat yourself on the back. That's a good one, because it's really easy to overlook this same material phrase. Not same mass, same material. So all these multiple choices a lot of times. In fact, any of you who've missed them, I think a lot of times just going over it. That's why I wanted to put this on video, because I really think that just when you you see somebody working out, you're like, oh, I even knew that, but I read it wrong. And there's something about what I'll call reading comprehension. And so, you read it, but what does it really mean to you? And that's not so easy. And so that's something you gain, by the way, with experience. And so if you didn't do so well on the multiple choice here, again, don't beat yourself up, especially on 18. But maybe it really boils down to reading comprehension. And so take your time and keep practice on these. It doesn't come simple, but it does take time and practice. And so usually the reading comprehension, students do better as the semester goes along. Now, I must say we get into some harder materials we go along too, so that also, makes things a little bit harder. But and we'll see that a little bit. We're going to get into Chapter 8 where I think we get some hard stuff. But then we also have some easy chapters coming in too. And very different too, because we've done mechanics, and we're about to shift gears from that. Well, I better keep going here. So here's number 19. 19 says, the law of universal gravity, the force blank as the mass increases. Well, again, that fits back up with the universal law of gravity. This is, in the numerator, so it's saying the force would get bigger as the mass gets bigger. You put a bigger number there, you get a bigger number there. And so that should be increasing. And so it would be, at this point, either A or C, and would blank as the distance increases. And so that should be a decrease. That's what we saw here. The number in the denominator gets bigger. It should be a decrease. And so that would fit right there, decrease. And so that would be C. So 19 would be a C. Also in this chapter was the discussion about tides. And if you remember from the video, I made a big deal to emphasize that tides were caused by the differential in force. That was important because you couldn't explain, maybe I'll put the sun over here, and then maybe moon in line with it. And so it's a new moon here. But you can't explain the bulge of water on both sides without getting into the fact that it's not the force of gravity, but it's the differential. But bottom line is you don't even have to really understand the differential part of it for this question. You just need to understand there'd be two bulges here. And so if you're sitting on this round object spinning around, you would move around and you would go into the bulge. That'd be high tide, and 6 hours later you would go where the water's missing, so low tide. 6 hours later you'd be high tide, and 6 hours later you'd be low tide. And so you'd have two high tides and two low tides, and that would be then D there. What is the high tides and the low tide? And then which has a greater momentum? And so we got 4 left here, and so this brings us to our last and final chapter here, chapter 6 about momentum. And read this one carefully: a heavy truck at rest. Now remember, a momentum is mv. So if they say at rest, v is 0 and has 0 momentum. Whereas a rolling roller skate may not have much mass, but at least it's moving, so it has some number here. So it's some number small times some number small, which has a small amount of momentum, but that's still more than 0. And so it would be the roller skate there. And this is one that students could easily confuse mass with momentum. Momentum is both of them. It's not just big mass. And so truck has, heavy truck has lots of mass, but that doesn't make it a lot of momentum. The other factor is speed. Here, a stunt person who is shot by a bandit and then falls from a balcony into an airbag rather than onto the ground will not get hurt. And so why? Because and if you look at something falling, and so here's the stunt person falling, they're going to have to go from whatever speed. So let's say they fall from, I'll just do 5 meters up because we know that takes 1 second. And so they would be going a speed of 10 meters per second when they hit that airbag. And they're going to need to come to a stop. And so you take the mass of that stunt person and then their speed, 10 meters per second, minus 0. They need to come to a stop. So the change in momentum is going to be the same, whether they hit an airbag or whether they fall on grass or whether they fall on concrete or whether they fall into a lake. The change in momentum is still the same. So because of that, A says the momentum change will be less than falling into an airbag. No. It's falling into an airbag rather than the ground. The change in momentum is still the same. You go from some momentum to 0. The momentum is less for the airbag. Not even real sure what that means. The airbag doesn't really have a momentum. It's not moving. It's the stunt person that's moving. Now here's one. Impulse is less for the airbag. Impulse is a fancy word. I'm not sure if I got a chance to use it. It just means change in momentum. But again, I'm not sure why you would say the airbag would have any change in momentum. The airbag doesn't even have any momentum. But this is like that happy ball and sad ball. No, I'm sorry. No, it's not quite like that one. It's more like the one I was discussing of catching the water balloon or the egg or the baseball. You wanted to then reduce the force on your hand, and you do that by increasing the contact time, because these two have to come out to be the same number. That's what I was trying to say. The change in momentum, whether you hit the ground or an airbag, is the same. But that doesn't mean the force and the time has to be. And anything with a bigger time would then have a smaller force. And that's it. Increasing the stopping time, getting that number bigger, will make a smaller force because this is the same. Yep. So that's really the golden ticket right there. And so it is D. Here's a good one, and both of these are conservation of momentum, the 23 and 24. Here, if rockets are fired from an airplane in the forward direction, the momentum of the airplane would be. And so if I had an airplane flying along, something like this, and then there's rockets mounted on it, that has a certain amount of momentum. And so if the rockets go shooting off forward, the rocket itself gains some momentum. And remember, the total can't change. So the airplane itself must lose something. So I think the key to this problem is to remember conservation of momentum is the momentum is the same for both of the objects, or all of the objects if there's more than two. We've been focusing on two as we are just learning this. But if the rocket then gains momentum, the airplane loses it. And again, they're not talking about the whole, what we call the whole system. They said the momentum of the airplane. So the momentum of the airplane will decrease. And so essentially the airplane is giving up some of its momentum and giving it to the rockets. And then finally, the last one with some numbers is really kind of like this airplane with the rockets. Here we have Juan standing on this giant skateboard. I'll just make this giant skateboard, and here's Juan. Put him to one side of it. And so Juan has a mass of 60 kilograms. The skateboard has a mass of 30 kilograms. But Juan has a mass of 60 kilograms, standing on a giant skateboard. And initially at rest is a key. So if we made a little chart of before and after, we would say, okay, before Juan does anything, Juan and the skateboard together are not moving, and therefore they have no momentum. And so I would say before Juan does this little walking bit, there's no momentum. And so then there would be an M1, V1 for Juan, and an MV or M2, V2 for the skateboard. And then these two have to add up to be 0. So one has to be positive and one has to be negative. And so it says here, if the speed, what is the speed of the skateboard if Juan walks to the right? So Juan begins to go this way to the right with a speed of 3 meters per second. So, of course, then the skateboard has to go to the left. And so one has a positive momentum and skateboard has a negative. That's the only way you can get to 0. One is positive and the other one is negative. And so one, if you calculate the momentum of one, it's 60 times 3. Let me just check. Is that right? Yeah, 3 and 60. Okay, so this is 180, and the units are kilogram meters per second. So again, that means this has to come out to be 180. And to the right is 1, so to the left would have to be the skateboard. Although I don't think we have to care about the direction, because it just says what's the speed of the skateboard. All right, so if we've got 30, it'd be 30 times what speed? And then so if we bring the 180 to the other side, we also divide by the 30, we would get the speed. Of course, bringing it to the other side technically makes it negative, but then we would get 6. And so 30 times 6, sure enough, is 180. And technically a negative 6, so negative 180. So one has a positive 180, and the skateboard has a negative 180. And so one goes one way, skateboard goes the other way, but it looks like the answer would be then C. All right, well, I'll call that a wrap here, and I'll work on part 2.